Everybody, Gary Kessler here from Fathom 5. Welcome to a presentation here on AIS Protocol internals. The reason this is an abridged talk is because originally this was designed as a 4-hour training session. Maybe we'll do that next year. And it became instead a 45 or 50-minute talk. So I'm only going to talk about certain pieces. And so without too much further ado, for those of you who don't know me, again, my name is Gary Kessler. I am a principal consultant with Fathom 5. I'm also very active in the Coast Guard Auxiliary, where I'm the chief of the Cyber Augmentation Branch. Also doing some work this year next as a non-resident senior fellow with the Atlantic Council, and I'm a visiting faculty member online with the Coast Guard Academy. I keep reminding my wife that I'm retired, or actually I guess it's my wife who keeps retiring or reminding me. But in any case, I also wrote a book on maritime cyber, came out last year. And what I really like to do is spend as much time as I can in, on, and under the water. So I'm a scuba instructor with a captain's license, which tells you why I'm living in Florida. Anyway, here's what we're going to talk about today. The grayed out stuff is the stuff we're actually not going to spend too much time. I don't know why this is advancing on its own. Where I'm really going to focus on the AIS protocols that are used for broadcast transmissions, because that's most of what we're going to see looking at stuff on the air. There's a bunch of other stuff to talk about, but I'll save that for another time. So let me give a quick AIS overview. Most of you, if you're here, you probably already have a good view of AIS anyway, but the reason I want to give a little bit of an overview now is just to sort of put your head in the direction I want it to be when we're thinking about some of the detail we're going to talk about. So first of all, AIS is a situational awareness tool. It is a tracking system that's used by traffic management systems and maritime authorities and shipping companies for that matter, and ships themselves, so that they know about other ship traffic that's in the area. And, not only do they know there's another vessel, but they know things about the vessel, like the course of the vessel, the speed, its rate of turn, intended destination. Possibly you'll know something about the cargo type, you'll know about the ship type. So if you think about radar as giving you a blip that tells you there's a vessel over there, well, what you're getting over here is a lot more precise information. AIS really came out of the wreck of the Exxon Valdez back in 1989. We didn't really start to see AIS for another 10 years or so, but the point is, this is a system that was designed in the late 80s, implemented in the 90s, and if we talk about any security issues, it'll become real clear why this was not intended to be a secure network. Anyway, this is the kind of stuff you'll see with a display that is showing you AIS information. So for example, right there in the middle, you've got the Ocean Spirit. Well, not only do you know something about the Ocean Spirit by name, but you know its speed, the type of ship. Let's see, 7.2 meters could well be, I don't know, could be its draft. Anyway, and where it's headed. And again, you can get all sorts of different information. Hopefully they'll give you a better key on a lot of this. So like I said, what I want to focus on here is really the protocol architecture and the standards that you need to be looking at if you're interested in building products, receivers, transmitters, what have you. And primarily, well, this picture was just sort of supposed to be a stand-on picture here. NMEA, the National Marine Electronics Association, 0183 is the primary standard that I'll be talking about. NMEA 2000 is the primary standard that you will see on a lot of big recreational ships. So commercial vessels are still using a lot of 0183. Yachts are using, NMEA 2000. But the point that we're trying to show here is that you can hook up lots of different types of devices onto the communication standards backbone, and almost everybody is in fact using NMEA standards for that. So let me sort of give you a little brief rundown here. NMEA standards were primarily designed for inter-device communications on board a vessel. So this is communication within the ship, within the skin of the ship. NMEA 0183 came out in 1983. The latest version of it is from 2018. But basically, it is a text-based communication protocol. It runs at relatively low speeds over things like, RS-232, RS-422 serial lines. And again, you can see the speeds there, 4800 or 38.4. The IEC has also adopted NMEA 0183 as a standard. And you can actually get this standard either from the IEC or you can get it from NMEA. In about the turn of the century, NMEA 2000 came out, and there was a redesign on the messages. They now use parameter group numbers. It's a lot of stuff that came out of the controller area network bus work, the CAN bus. And so the messages now were binary messages operating over the CAN bus at, you can see here, much greater speeds, 250 kilobits per second. This has also been adopted by the IEC as a standard. And where we find ourselves right now is the latest standard from NMEA is OneNet. And OneNet also uses PGNs, but instead of running over the CAN bus, they're running over IP version 6 on top of Ethernet, which means, of course, I can get gigabit speeds. And they also employ IPsec for security. So NMEA, when NMEA 2000 came out, there was not a real intention necessarily that 0183 would be replaced. This is just sort of, the suite of tools that are available in their standards. Now, OneNet is almost unique among maritime communication standards because, again, it employs a secure mechanism that is useful because although this is designed for inter-device communication, there's all sorts of ways where presumably from the outside, I might cause a device on the inside to send spurious, nefarious messages, or an insider could also, do that as well. In any case, down at the bottom in blue, I talk about ITUR, the International Telecommunication Union, radio communication sector, their recommendation M.1371. M.1371 describes AIS transmissions over radio. And the reason they're really important right here is because they're employing NMEA 0183 formatted messages at 9600 bits per second. That's what we see over the air. So I told you that so I can show you this. Here's a picture of a boat. And is just trying to give you an idea of all the different types of devices that might be connected on a boat. And in this case, they're using an NMEA 2000 bus for all of them to communicate with each other. But you'll also notice in the lower right, there are gateways between NMEA 2000 and NMEA 0183. So, non-NMEA 2000 devices can talk to each other as well. But the reason I showed you that is because I really want to talk about this. So as a situational awareness network, it's important that ships are able to communicate information to other ships and possibly to ground stations. That's where, maritime authorities come in. But they can also communicate in some cases with search and rescue ships and aircraft, if those ships and aircraft are appropriately equipped with AIS. And then, of course, there's satellites. Now, what this picture here is trying to show with the green lines and the dotted green lines is all of these devices that are, communicating with each other effectively in real time. You don't necessarily have real-time communication with AIS over satellite. Frequently, what you have with some of the satellites that are getting some of the historic information is they are gathering AIS information as they receive it when they're over water. And when they get back into a position where they can download to a ground station, they're downloading a whole burst of information. So you were getting historic information, but not necessarily real-time information. Now, I make reference here to a Class A vessel, and I probably should also make reference to Class B. Class A vessels are those vessels that either due to their operational capability, their size, the number of passengers they have, or other things. They are required to have AIS. Class B are other vessels that may carry AIS, which is anybody, but they're not required to. And while I'm not going to get into it a lot here, there are requirements for how frequently a device needs to be transmitting. And Class A devices need to be transmitting, as you might imagine, since they're required to. They're required to transmit at least every 30 seconds. And if they're going fast and or maneuvering, it's possible they may need to be transmitting up to once every 2 seconds. Whereas Class B devices don't have to transmit anywhere near with that frequency. So here is my take of the protocol architecture related to AIS. So at the top here, I've got my AIS data, whatever that data might be. It might be input from sensors telling me things like, well, as I said, rate of turn, speed, my course, my heading, the name of my ship, the type of cargo that I have, all the kinds of things that could possibly be associated with AIS. Now, the AIS data in most practical uses is going to be formatted either into these so-called encapsulated ASCII sentences, or they're going to be transmitted or formatted in these AIS parameter group numbers that I mentioned before, the binary messages. Now, if I just track the encapsulated stuff, if I am using AIS devices within a vessel, and I'm using NMEA 0183 or the IEC equivalent, I'm going to be running over EIA 232.422 serial lines, and again at a speed of 4,800 bits per second or 38.4 kilobits per second. If I am transmitting stuff over the air, then I'm following the ITU M.1371 recommendation. And what's going to happen is my messages are going to be encapsulated into HDLC, broadcast out over radio, one of those two frequencies at 9,600 bits per second. And there's going to be some form of time division multiple access algorithm that we're going to use so a device knows when it's going to speak. AIS is a purely peer-to-peer network. There is nobody in charge saying, it's your turn, what have you. So the TDMA schemes all have to be some sort of mechanism so that ships can transmit and they know when to transmit, and we minimize the number of collisions. I'll make a little bit of passing reference to that in a second. Anyway, if you have AIS PGNs, PGNs are going to be transmitted, if you're in NMEA 2000 standard, over the CAN bus using CAN 2.0B framing. And I'll show a little picture of that later on. And then we'll run the CAN bus frame on top of the CAN bus physical layer at up to 250K. If you're following OneNet standard, which is just emerging now, and I don't know that there are any products yet, but if there's not now, there may well be by the end of 2020, except for the fact that we're currently in 2021, aren't we? Well, whatever. AIS PGNs are going to be carried in an IP version 6 packet, and that packet, of course, is then going to be carried in an Ethernet, and then we have the medium access control and physical standards that are part of Ethernet, and of course, that's where I get my enormously high speed. Just as a little bit of a, a spoiler or, foreshadowing. There are some devices that are pumping out so much information so quickly, they can't work with NMEA 0183. And in fact, they might even have difficulty with NMEA 2000 because there's limits on the size of the transmission in addition to limits on the speed. So, for example, a device like radar, which is pumping out a tremendous amount of information, is nicely suited to something like OneNet because, I can have a larger packet and I can have really huge speeds. So again, just concentrating on broadcast AIS. So here's my picture of AIS over VHF. Again, it's in M.1371. M.1371-5 is a reference to the fact that this is the 5th version. And if you go online to download this, you want to be sure you get the -5. Again, here are my 2 radio transmission my two radio frequencies. So I mentioned before TDMA, so I should slow down just a little bit to talk about that. The most common form of TDMA that is used in AIS, particularly on over the air, is something called self-organized time division multiple access. And basically what happens is when a ship enters range of where it's going to start talking to other ships, it listens on these two channels, what's known as channel A and B, and it listens to the time slots. There's fixed time slots, as it says there, 26.6 milliseconds is a time slot. And you wait for an empty time slot. And when you find an empty time slot, you can transmit and you can also reserve additional time slots, because the rules are when you enter the area, you need to listen for some number of minutes. And so you can sort of get the lay of the land. And once you get that lay of the land, you can now say, okay, folks, this is the slots that I'm going to take. Hence the self-organized TDMA. And there's some pieces of this SOTDMA that actually appear in some of the AIS messages when devices are trying to get themselves a time slot. So I've already given a little bit of an overview of 0183. I'm not going to beat you up and do it again. I am going to focus on what kind of stuff we see over the air, but I want to take a tiny bit of a diversion. I have here a list of NMEA 0183 GPS messages. The reason I am showing you GPS is because this stuff is all over the internet. You don't need to read the standard, which is proprietary. You can go online to tons of places. But this gives you an idea of what the content of a GPS message might look like. And I'm going to go one step forward and give you an actual sample of one. So this is a GP-GLL message. The GP, first two characters, identifies the talker and says, this is the global positioning system. So this is a GPS message, as opposed to a GLONASS message or a Galileo message. The message type is the next three letters, the GLL. So GLL means this is a message containing a geographic position, latitude, and longitude. And you'll notice you can read the rest of that message. I mean, if you know what it means, I mean, it's quite evident you can read it. I've got here somebody that is at 29 degrees, 11.585 minutes north, 080 degrees, 46.181 minutes west. You can see the time there. It's 1:50 and 30 seconds UTC. And now the rest of it, you sort of have to figure out, do I know what this means? But the point is, you can go online and you can see all this stuff. Now, I want you to notice that this message begins with a $sign. This is a so-called parametric message. So the parameters, it's plain view, hence the $sign, and all of the parameters are comma separated until you get to the very end where there's a checksum, but we'll talk about that more later. Now, there are parametric AIS messages. I know this because I've seen them in the standard. And this one in particular, I have actually seen from a public source. This is a VSD message, and you would think that I would have remembered what VSD stands for. This is something about vessel ship description, I think. But in any case, you'll notice after the VSD, I've got this, A, B, C, D, and all that stuff, with commas. Those are the different parameters. But I have information here telling me the type of ship, the draft, number of people on board, the destination, et cetera, et cetera. And down at the bottom, I have, a sample AI VSD message. And you can go back and you can figure out what the parameters are. Now, I told you that merely so I can tell you this. I have never seen one of these in the wild. What we see over the air is stuff that looks like this. So this is display from OpenCPN. If you haven't played with OpenCPN, you should absolutely go get it. And so I have a ship here, the one at the bottom there that has that square bracket around it. This is the slotation. And you can see the kind of information that we can learn from the slotation. But if you look at the debug window there, sort of, top there in the center, I mean, that is what an AIS message looks like over the air. And all of the ones I've ever seen in the wild, they all look like that. And so what I want to do basically is sort of walk you through how you could create this. I probably should have unplugged from the internet. In any case, like I said, this is what an AIS message looks like. Most commonly, we're going to see an AI VDM message. And I'm going to tell you what all these piece parts are. So the exclamation point at the beginning says, this is an NMEA formatted message using special encapsulation. So instead of the $sign, and you can sort of read things, this is, well, you're not going to be able to read the payload here. The AI VDM identifies the talker ID. AI says this is a mobile AIS station. VDM says this is a, an AIS radio data link message. Now, the next 3 parameters are all about classic fragmentation. This transmission here is called a sentence. A message can be composed of multiple sentences. So the first number there, that in blue, that 1 says how many sentences are in this message. So in this case, it's 1. And so the yellow is saying, well, what sentence number is this? What fragment number? Well, since there's only 1 fragment that we're going to have, this is fragment number 1. And the next number is a serial number, and that's null. But now imagine, suppose I had 3 sentences, and this was fragment number 1. Well, the only way I can reassemble is if I have some sort of serial number. So I might have there, instead of a 1-1 null, I might have a 3-2-7-9-8-5. Again, telling me how many total sentences do I expect, which fragment number is this, and what's my serial number for reassembly. The next character is either going to be an A or a B, and this identifies which channel are we transmitting on. Remember, there were 2 frequencies. One of them is designated A, the other one's B. And then I have that long list there, the one that starts with the 11C2 and ends with the 0000. That is the encapsulated payload, and that is so-called armored ASCII. And I'm going to step you through the creation of one of those things. Now, I need my payload to exist on 6-bit boundaries. So there needs to be an even number of 6-bit blocks within the encapsulated payload. So if my payload is smaller than 6 bits, I'm going to have to add some padding bits. So the first green number there at the end that says number of padding bits for 6-bit alignment. How many bits did I need to add to the payload so that I got a 6-bit boundary? So that number obviously is going to be some number from 0 to 5. And then you have the asterisk. The asterisk indicates the field that follows is the checksum. And so there is the checksum, 6A. We'll talk about how we get that later on. Now, I'm going to live dangerously and try to go to the web. It's trying to. There we are. Okay. The very best reference for knowing how to encode and decode AI VDM and AI VDO messages is this website by Eric Raymond. And you can see the URL up there at the top, and I put the URL in the reference list as well. And you can see there is a ton of information here about all of the different message types, the different payloads, how stuff gets encoded, all that kind of stuff. I'm not going to scroll through this right now, but I am going to actually make reference to it. So your real choices are going to the standard, going to Eric Raymond's site. And frankly, you should probably go to both. The standard, however, is the definitive right answer for things. Turns out that the standard has some ambiguity. And some of that ambiguity has been addressed in Eric's page, because he'll say, the standard's ambiguous about this, but this is what we see in real life. So anyway, so you need to know about that. Here are the 27 different types of AIS messages defined by ITU recommendation M.1371. I'm going to focus on message types 1, 2, and 3 today, because I want to show you how to put together a position report, Class A position report. But you can see that there's a whole ton of other types of messages down here. Now, for radio transmission, basically, the way we're going to create one of these AIVDM messages, we need to have whatever AIS information that is pertinent to the message type we want to create. Then what happens is we take the data, it's going to be encoded in binary. So we create a binary string. We then need to take the binary string, and of course it has to be padded, but we take the binary string, we're going to break it into 6-bit bytes, and then we create something called an armored payload string. If the message is longer than 372 bits, we now need to fragment it into 360-bit fragments. So remember, a sentence is going to be limited in its size, and the message, may be significantly larger. Then we add some additional overhead, and I'll show you the overhead later on. In fact, I'm going to show you all 5 of these steps. So let's start with this. We're going to be doing binary encoding. Each parameter identifies what type of data type it is. And I'm not going to read all this to you, but you can sort of get the idea. We've got signed and unsigned integers. We've got Boolean. They have something that they call an enumerated type, which is a cute way of saying there is a table and you must choose a value out of the table. So for example, if there's a 4-bit field and it's an enumerated type, they will give you 16 possible values and they'll tell you what each of the 16 mean. Anyway, and then you might have a data string, or you may just have data, character string, or just, binary data. All 27 messages start with the same 38 bits. They start with something called, they start with the message type encoded in 5 bits, which makes total sense as there's 27 message types. There's a repeat indicator, and actually this is one of the things I think is rather ambiguous what it's used for. Almost all the time I see it, it's set to 0. And then there's something called the MIMSY, the Mobile Maritime Service Identifier. The MIMSY is the identifier of the transmitter. In general, MIMSYs are associated with ships, but in fact, the MIMSY is tied to a device on a ship. The IMO, the International Maritime Organization, gives every ship a unique hull number, and the hull number stays with the vessel for the lifetime of the vessel, even as it changes names. The MIMSY may or may not. It may move to a different vessel, or it may stay with a different vessel as the vessel changes its name. In any case, you'll notice all the formats here for the MIMSYs. So the one that we mostly see is the second one there that says ship. And you'll notice it starts with something that says MID, M-I-D. The MID is the maritime identification digit. And the MID is assigned also by the ITU, the International Telecommunication Union, and numbers between 201 and 775 identify a country or some sort of maritime authority. In most cases, it's a country. And so effectively, it's a country code, just like we have with telephone numbers. So the US MIDs, I think, 369 is certainly one. I think 368, maybe 367 are also MIDs that are assigned to the US. In any case, a ship is going to have a MIMSY. They're all 9 digits. The first 3 digits will be the country code, and then 6 more digits. And then you can see the different formats that you're going to have there of different types of MIMSYs. So like I said, what I want to do is I want to show you step by step the creation of a Class A position report. This is a type 1 message. It is actually one of the most common messages that you're going to see. And I like it because it has 16 fields, but it's got a half dozen different data types. So I can show you a lot of stuff. So again, what I'm going to do is I'm going to show you how we create the binary string that is this message, convert it to armored ASCII, and then create an AIS message that you could then transmit and actually parse it, and you're going to get the right information back. So here's all the information I need to know about this message. Again, this is a Class A position report message. So, I've made up the MIMSY. I don't think it belongs to anybody, but I'm not sure. But I need to know, what is my navigation status? In this case, I'm underway. I've got a rate of turn sensor telling me that I'm turning at 15 degrees per minute. My speed over ground is 15.5 knots. There's a longitude and a latitude. My course over ground is 056, whereas my true heading is 060. And I got some other stuff that I'll repeat later on. But a position message is going to contain all of this information. So that's why I'm putting this all up here. If you go to Eric Raymond's page, or you go to the M.1371 recommendation, and you see the table that tells you what's in a type 1 message, actually type 1 through 3 are all the same. This is what you're going to find. So this tells you how big is the field, which bits, what is the data type, and then how are you going to actually fill this information. So for example, on line 1, the message type is an unsigned integer, and it's going to be a number from 1 to 3 based upon, are you doing a type 1 through 3 message. You'll notice as you look down the units column, you got a bunch of stuff that says see below, because there is a lot of explanatory text telling you how you really have to encode this stuff. So moving right along, we're going to start with the message. So remember, every message starts with the same 38 bits, the same 3 fields, the message type, the repeat indicator, and the MIMSY. So if you look at the top there, the message type obviously is a 1. Repeat indicator is going to be 2. And then the MIMSY, well, we've already decided that 369.321.749 is going to be our MIMSY. What I have in the middle there for programmer types is a code snippet that would tell you how you would start to create your payload string by taking those 3 values, converting them to binary, and just concatenating them. For those of you who are not familiar with the sprintf function, this is a way of formatting output for the print function, but in this case going into a string rather than going to an output device. So the first parameter there is a format, and the second parameter is actually a number. So in the first case, I'm taking the type, and I want to make sure it's an integer because I don't want somebody to give me a type 1.4 and then I get confused. And I'm going to convert that to a binary output with 6 digits or 6 binary digits and leading zeros. So that's what those sprintfs are doing. And then the bottom is showing, well, what does the binary output actually look like from each of those sprintfs? So you sort of get this coming and going. And if you do decide to build any code, hopefully this gives you a way where you can check stuff out as you're building. The next thing we have are 4 bits of the status field. The status field tells you navigation status. This is one of those enumerated fields. It's 4 bits, so 16 possible values. Well, here's what all 16 possible values look like. Value 0 means you're underway using the engine, and you can obviously read everything else from there. So I'm going to take the navstat, need to convert it to a 4-bit value, and there's my 4-bit value. Then I have the rate of turn. So rate of turn is one of those first ones you come across that says see below. So the value that we have from the sensor is that we are turning 15 degrees per minute. The rate of turn actually has to be transformed. And if you look at the text at the bottom there, where it starts to say values between 0 and 708 degrees per minute. So what happens is the way they encode is they take the value of the rate of turn indicator from the sensor. They take the square root of that value, multiply it times 14.733, and that gives you the rate of turn indication that will be encoded in the AIS message. I'm not sure why they do this. I've not read anything that's explained that, but this is what they do. Now, this also has to be a signed integer, because if it's positive, it means you're turning to the right. And if it's negative, it means you're turning to the left. So they come down here and I say, okay, the sensor rate was given to us at 15 degrees per minute. The AIS encoding value is going to be the square root of 15 times 4.73, which gives me roughly vaguely 18. But again, for you programmers, I need to explain the sprintf here, and I need to explain the comment that says multiplying by 2 times the field length minus 1 preserves the sign. So here's the problem, at least in Perl and possibly in other languages as well. Let's say I have a 32-bit word, and let's say my value is negative. What Perl is going to do is it's going to extend the 1 from the negative all the way out, all 32 bits. But this field is an 8-bit field, and I only want 8 bits for my rate of turn indicator. In Perl, even if I have this construct and that format saying 8 bits, it'll try to encode all 31. So by multiplying the value times 2 to the 8th, 8 being the field length, 2 to the 8th minus 1, I'm ANDing. So that means everything above the 8th bit becomes a 0, and everything below the 8th bit stays whatever it was, and now this fits into an 8-bit field. So we're going to see this idea of multiplying times 2 times the field length minus 1. We're going to see that several times here. Anyway, if you do this sprint F and you've got the value 18, this is what's going to get encoded, what you see there on the bottom. Speed over ground is going to also be, what they're going to have here is that the U1 is indicating that I'm going to encode an integer, but the integer is actually representing a floating point number. So the speed over ground is knots in 0.1 knot resolution. So if I want to encode 15.5 knots, the number that I want is 155, because we know we're multiplying by 10 and the parser knows to divide by 10. And then there's some special values. I can only encode up to a value of 102 knots, which is going to be quite quick. If you use the value 1023, this means that the speed's not available, whereas the value 1022 means you're going 102.2 knots or more. In any case, we're going 15.5 knots. And so you can see speed over ground is actually encoded as the number 155. Position accuracy, there's really only a couple choices here. They want to know whether you have, normal accuracy, which is to say unaugmented, which means, you may have greater than 10 meter error, or if you have something like differential GPS quality fix, which gets you within 10 meters. So this is either going to just be a 0 or a 1. Now I come to longitude and latitude. So longitude is given in this type of message as 1 divided by 10,000 minutes, which basically means you take the value of the longitude and you divide it by, what is that, 600,000. Now, the reason I'm saying in this message we have a 28-bit longitude. In other messages, the longitude may be of different length because they're giving different granularity. The rule is pretty much the same, used dividing by, a different amount. In any case, so longitude is a 28-bit value. In this case, this was the longitude that we were given, which was the 80 degrees, 53.479 minutes west. But we want to see that as a decimal degree, because otherwise we can't really encode it. So this is going to be minus 80.89131.666. We take that number, preserve the sign, but divide by 600,000. And then we encode what we have left there. That's why here, where I take my, my integer of my longitude, times the, 60,000 in this case, and I'm going to AND it with now 2 to the 28th minus 1, again, to, preserve my sign. If I then go to latitude, same kind of thing, except here it is a 27-bit field. So one of the reasons that it's a 27 versus 28-bit field, latitude can only run from -90 to +90. Longitude can run from -180 to +180. So I need more bits. Course over ground is merely going to be your course relative to true north with 0.1 degree precision. So again, if I want to encode 56 degrees, I'm going to actually encode the number 560. Just got stuck there. Here's my true heading. Yeah, I got stuck and it jumped ahead, way ahead. Okay, my true heading, 060. Again, going to be coded here just straight as the number 60. The timestamp, you always have a UTC time. And so this is going to be the number of seconds within that timestamp. And so in this case, 38. It'll just keep wrapping around from 0 to 60. The maneuver indicator is, again, one of those enumerated things. There's only, well, 3 valid values out of the possibility of 4. So in this case, I don't have any information available. So we just coded it as a 0. Then there are actually spare bits. Nature abhors a vacuum, programmers abhor spare bits, but somehow there's still 3 spare bits in this message. Probably this was to give it 168-bit alignment. But in any case, spare bits are always set to 0. So that's what we got. Then I have something called the RAIM flag. RAIM refers to the Receiver Autonomous Integrity Monitoring. And again, this is just whether it is on or off. So it's a 1-bit field, 0 or 1. And finally, we end with the radio status. Now, I'm totally copping out here because I don't actually encode this parameter. I just set it to 0. And so we're going to have 19 bits of 0. But in fact, at the bottom is the table telling you how you would interpret this field if you were going to parse it. So when I get real data and I parse it, again, this is the information that tells me exactly how I can understand it and take it apart. Now, after all of that, the question now is, I now have my binary output string. My binary string is the string that's formed at the bottom because we've been adding all those pieces. So now the question is, do you fragment or not fragment? Well, in this case, the payload string is only 168 bits. So obviously we can carry this in a single sentence. If it was greater than 372 bits, we'd have to split it into fragments. And well, we can do that at another time. In any case, we have 168 bits. So now we have to create armored ASCII. So we need to pad our message to be an even multiple of 6 if necessary, which we don't have to do here. And what we're going to do is we're going to convert each 6-bit block to an armored ASCII character. So in the M.1371 recommendation and in Eric Raymond's page, he has the table for what armored ASCII looks like. But basically, here's the drill. Up at the top there, I have my binary string, my 168 bits. What I've then done below there is I've broken the 168 bits into 6-bit blocks. Underneath it in blue, I have what the armored ASCII is. So 000001 binary is a 1 in armored ASCII. A 110110 binary is a lowercase n in armored ASCII. So from the binary, we get that armored ASCII string that you see below, the 15p equals W5, all that kind of stuff. So now I have my payload. So now I need the rest of the sentence. Well, the rest of the sentence is the exclamation point saying we have an NMEA 0183 message. We already knew we were trying to create an AIVDM message, so AIVDM goes next. We know there's only one sentence in the message. Hence, this is the only fragment in the message, and I don't have a serial number, so that gets me the 11 null. I'm going to transmit on AIS channel A because my device knows that. I have no padding bits, and 7.1 is the NMEA checksum. So I didn't say this before, but I'll say it now. The NMEA checksum is nothing more than an exclusive OR of all the characters after the exclamation point and before the asterisk. The asterisk is obviously then an important delimiter because commas delimit the various fields, but an asterisk says what comes next is the checksum. Well, the checksum covers everything before the asterisk and after, the first, well, in this case, the exclamation point. Like I said, it's merely an exclusive OR. So I'm going to give you a slight little brief, self-advertisement. I have a bunch of AIS tools to create these messages and to parse them. If you saw, I I'm giving this talk before DEF CON, and I'm not sure where this talk comes related to the AIS Tools demo that I have, but I've got a tools demo where I demo all my tools and how they can be used. And in fact, this message is probably one of the examples that I'm going to use. But I have a tool called AIS Ping. And so you can use my tool called AIS Menu and enter all this information, and it'll create you a message. Or you can use AIS Ping and take all the information, put it on with command line switches, and like I said, put in the same message, and you would end up getting the same AIVDM message. And the reason I showed you that is because one of my other tools is a parser. And so this is AIS Parser taking the same message we just had. You can look up here, it's the same message. And this parses it into all the piece parts, and presumably all of this information matches all the other stuff that we put in. Now, if you want to generate some NMEA 0183 data on your own, there's a really, really cool NMEA simulator that you can find online. There was an NMEA simulator that used to run only under Chrome. And within the last 6 months, they've come out with a new version that is not a Chrome plugin. It is a standalone program. It's actually pretty cool. And the nice thing is you can just run. And when I started running this the other day, I was in Sydney, and you can see the kind of information it's giving me, because I've got some AIVDM messages, I've got some GPS messages, I've got messages from a lot of different talkers. So it's really interesting. But you can also set, where am I? Where am I going? What's my speed? What's my rate of turn? And you can take control of the ship, hence generating your own information. Like, let's say you wanted to show a British ship going to a Russian port. You could put it into the simulator and you could create an AIS track. Just not that hard. Anyway, there are some other AIS protocols. This picture doesn't really mean anything. I like to have a picture on the separation pieces here. And I saw this and I said, well, there's some protocols I didn't talk about. I didn't really forget about them. But then I saw this headline: ship crashed after captain forgot about English coast. And I said, I have to use this picture. Anyway, I mentioned that there's all these other protocols. I'm not going to go into any detail now, but I just want to let you know, just sort of like foreshadowing. The physical layer, RS-232, RS-422, here's some information about the physical layer. If I want to take my messages that I just created, the sends I created, and broadcast it out over the air, well, there's some underlying pieces here as well. I mean, I need to format this into an HDLC frame. I then need to do all the radio stuff. I need to be able to do the self-organizing TDMA. So all of that needs to be done as well. NMEA 2000, I said, uses PGNs, these parameter group numbers. Here's an example of some output. This is from, I forgot to write it on the slide, but this is from the ActiSense reader. And you can see I have here not just AIS messages. I've got a bunch of different types of messages, but the one that's highlighted, the course over ground, speed over ground, rapid update, you can see some of it. Now you'll notice that there's not a lot of data with these messages. They're mostly limited to about 8 bytes of data. The reason being that NMEA 2000, oh, this is, by the way, how that particular message translates, but NMEA 2000 is carried in the CAN bus. Well, for those of you familiar with the CAN bus, and those of you who aren't, we'll probably have a talk about that at some point later on. The CAN bus only has a data field of 8 bytes. So I have to figure out how to get all these messages and slam them into 8 bytes. If they're bigger than 8 bytes, there's other ways whereby we put the messages together. So I'm going to close by saying a couple real fast things. I started doing these things with AIS messages and getting into the nitty-gritty of this stuff probably about 3.5 years ago. I was inspired by some of the work being done by Marco Balduzzi and his team at Trend Micro, talking about some of the AIS vulnerabilities, security vulnerabilities, and the Black Toolkit that they have. And their Black Toolkit is written in Python. I actually wrote a menu preprocessor in Perl that they have included in the Black Toolkit now. But I was interested in ways of securing AIS and building a model for security. And the only way I could do that was I had to generate messages, but then I also had to figure out how to parse them. And so I ended up writing, a boatload of code, which I really enjoyed doing. But for me, I've always understood systems by understanding the protocols. And if I understand the protocol, it has helped me understand the system a lot better. And so I've always, in that regard, if the bits are at the bottom, I've been a bottom-up kind of guy. And so it's really helped me understand security issues related to AIS. So with that, I think I've just hit my time limit. I wish everybody good luck, and thanks for being here. Have fun with this. I will be available one way or another for Q&A, either live via Discord or Slack or whatever platform they're going to use at DEF CON, or by email. I'm always delighted to help out with emails on this stuff. Just show you the last couple of pages. Well, there's my summary page. All the acronyms and abbreviations are going to be here in the slide deck. I do have some references of other things you might want to read. And with that, I am pretty much done. So I thank you all very much.